Sorry about that. So, yeah, for all those who listened to this recording, there was a very nice introduction, but you missed it. Yeah, so the reason we are interested in it is this unstable configuration combined with the fact that it contains a lot of ice. So we are interested in what is the future scenarios for Thwaites Glacier. Can it potentially disintegrate rapidly in the future? That is the reason why we have this huge project. This is the largest project that has ever been funded in Antarctica, the largest research project, money-wise. And it has run over some years, and it will continue for some years with several expeditions by air and sea and land. Okay. So this is a satellite picture of what it looked like when we were there. We were exceptionally lucky. We were the first trip that could enter this area. So this picture is skewed. It's north this direction. So we are looking at an area here that hasn't been open before, actually. While we have had satellite records, usually there's icebergs and sea ice stretching all the way out here. So this area here had never been visited before. And it just magically opened for a few weeks when we happened to be there. So we actually rearranged our plans. We had originally planned to go to Pine Island Glacier first and do most of the research there. But when this opportunity presented itself, we changed and went here instead. And we could do research here for 2 weeks, and then suddenly everything changed. And this was on March 2nd, and this is on March 6th when things started to happen. So all those icebergs that are pressed up here, for some reason, they let go, and everything here, there was an armada of icebergs that rapidly moved out, and the captain told us we have to evacuate and leave the area, and we had to leave some instruments behind in the water, actually. So it looks dramatic when you look at from above, from the satellite pictures, but we didn't really notice. We only saw, that's strange, that iceberg wasn't there a few hours ago. So, but the captain had control, luckily, of what was dangerous and not. So this is the view when we were there, a photograph from the dreaded, it's called the Doomsday Glacier in Namibia. Glacier. It was perfect conditions for AUV operations. And it takes some time for the satellite images to get in, so we had to operate mostly by the radar images. And this is the ship track. Yellow here is the ship track, and those colored tracks here is our AUV tracks. But we did 13 missions all in all, and I'm going to tell you the results about this one, the purple, and the brown one here. Those went partway under the glacier. Okay, and the reason why we have these lines going back and forth is that we did some multi-beam surveying with the ship as well. For some reason, it's lagging. I don't know really if it's the internet or why it's looking like this. Okay, this is a map of the area where we visited. Up here is this is the first AUV mission, and this is the second. And here you see how this glacier stretches. So here it's grounded, so that means it's resting on seabed. And this whole part here is floating, and here is the grounding zone. So below here is the continent of Antarctica, and everything is resting on land, presumably. We don't know, maybe there's an underwater lake, under ice lake here, which the radar people will tell us about in a few years. And this here is so-called shear zone. So the ice east of the shear zone is not moving very much. The reason for that is that it's stuck here on this underwater island, and the ice west of the shear zone is moving quite rapidly out towards the sea. And this is here is the area of the radar images that you saw. So all those icebergs, they were pent up here, and then they started to move away. And when the icebergs move away, the ice feeds on. So this ice is moving a few kilometers per year out towards sea, and this one is basically not moving. So that is called a shear zone in the ice. Yeah, and here is the image of the, here is the velocity of the ice. So red means fast and blue means slow. Yeah, so if we start with the easternmost of those troughs, this was the deepest trough. Here you see the AV tracks, and the color is temperature of the water. Red means warm. Warm in this area means 1.2 degrees. The freezing temperature is -2, so it's not really swimming temperatures, but it's warm in comparison to the rest of this area. And this was the first big results that we got, because we didn't know, we suspected that warm water is entering under the glacier through these troughs, but we hadn't seen proofs before. So we got some solid proof that is happening. We also got some velocity measurements from the acoustic velocity, Doppler velocity logger. And we see that the water is flowing quite rapidly in towards the glacier in this trough, 10 to 20 centimeters per second. That is also a lot in this context. And this is the westernmost trough. We didn't go very far in, only 700 meters below the glacier. And this trough is divided into two, so, and in both of them we found warm water. And here we also got some velocity data, and we see that the lowermost part of the water column is moving in at about 5 centimeters per second to the glacier. In this first mission, we went further in. This is about 3 kilometers, this distance here. So we went in, we obviously did the other one first, and then when that went fine, we sent it in again a little bit further, and we did some surveying here. So we went back and forth a little bit. Got some really nice data. Here it wasn't so deep also. This one went to 1,100 meters, I think, at the deepest point. And here we stayed around 700 meters, the whole mission. And these, we try to combine our missions so that we do several things and minimize the number of launch and recovery operations, because that is the biggest risk for us. So this lawnmower pattern here was done to get some geology data. So here we did mostly multi-beam surveying, and then we combined it with these hydrographical surveys where we looked at ocean currents. Those two. Okay. What we do, I'm a physical oceanographer, and one common thing that we do is that we plot salinity and temperature, and salinity and oxygen and temperature. The reason for that is, first of all, they are easy to measure, and we can have good calibration between instruments over time and over space. So there is some good base work for those parameters, and also they are conserved so that you can change temperature and salinity and oxygen at the surface, but once you have left the surface, those are conserved. So the only way to change it is by mixing with other water masses once the water has left the surface. So if we have 2 water masses here, so this one here has salinity 34.9 and oxygen 4.4. And if we mix that with a less salty and slightly more oxygenized water, 34.1 in salinity and 5 in oxygen content, then all the mixtures between those two water masses should lie along a straight line. And then you can think, what happens if we mix it with glacier water? Then you also change the heat content, because in order to melt ice, you need latent heat. You lose latent heat, so you lose temperature and add a little bit of fresh water to the mixture. And that, so the mixtures of glacier water and ocean water, they will always end up. This is the ocean water. And when you mix it with glacier water, when you melt ice, you will end up on this black line here. So this is calculated theoretically by a Norwegian many years ago. And it's also clear from all the data we have that this is correct. This is how it works. So when we compare the two troughs, blue is the eastern one, where we went deepest and longest under the ice. And the red is the one where we only went a little bit. You can see that the red water contains more meltwater, and also interestingly that they are quite separated in oxygen and salinity and temperature space. So they are not directly in connection with each other. And if you zoom in a little bit, so this is the deepest water. Out here is the surface water. You have a larger spread. You are nearer the surface, so other things happen. But here you are far away from the surface, so they collapse on a single line. If you zoom in and only look on the deep water, it looks like this. This comes first. If you now include, we measure these parameters also with the ship. So all those dots are stations where we went with the icebreaker, and the colors here correspond to colors in this data. Then you can see that this spread that we noticed between red and blue, it's also present outside the glacier in the ocean. So blue and green colors, they are here in this deep troughs, and pink colors, they are out here in this trough, which is connecting to Pine Island Glacier further down. So they are separated also outside. And if we zoom in now on the deep part, it looks like this. So if you look even on the deepest part, you see here that there is a branch of low saline water that is only found in Pine Island Bay and by Ran in this mission here, and in this one CTD station that we took with the ship, the red one here, which was virtually next to the ice wall. And that tells us that this water here that has those properties in salinity, oxygen, and temperature, it has come from Pine Island Bay. So there's a connection, a deep connection between Pine Island Bay and the front of Thwaites Glacier. And we did not know about that. We, of course, have never been here before, so no one has measured the depth in situ, but we have had some guesses by sending very accurate gravity sensors above, and then you measure, if you have a shift in the gravity, you can guess that there's a big mountain or something below here. And based on those data, there should be a ridge here that blocks any deep connection. So all the models, they think that the main entrance for warm water is through the north, and this is the water that controls the melting of the glacier. And what we found is that it's equally important, or maybe more important, what happens to the east here, near Pine Island Bay. That means also that Pine Island Bay is a key region where you should look. If things happen in Pine Island Bay, it will affect the Doomsday Glacier also. And this is a summary of our findings. This is the main flow paths. We don't know, we only see the water here and in a stretch here. We don't know, does it enter here or up here? If we suspect both, dynamically it should be hugging a coast like this, but also dynamically this is the deepest connection here. And then we also saw some traces of quite vigorous mixing when those two water masses meet. This water is denser than this deep water, but this water is found at a deeper down. So when they meet, you have dense water here and light water here, and that should create some quite rapid mixing. And then we also saw this meltwater that exited here in the west. Okay, that was our. Oh yeah, I have one more thing to show. I did have a movie. I realized. I hope it works. So this is you remember the lawnmower pattern. This is what we found there. So this first picture shows the multi-beam data from the ship, and this is what you normally get from Antarctica, this kind of resolution. And from this is quite high resolution, actually, in comparison. Based on this, you can guess what happened in the past with the ice and what processes were active when the ice was last scraping over this area. And with our AUV, we got order of magnitude better resolution. So this is the same region, but with data from Bran. So as you see, you get a whole new level of information. This kind of resolution we haven't seen before from this area. And it's also an area that was quite recently covered by glaciers. So all those tracks, it's quite unique that you can observe the tracks with such high resolution in such quite near time, so to say. And this is another very interesting study that is in progress now. I hope it will be submitted soon, working on this bathymetry data, together with mostly American geologists. Okay. So problems we had an upward-looking sonar, an MS-1000. It didn't work. We got crap out of it. We had a lot of work mounting it and downloading data and so on, and nothing, we couldn't get any information from it. The resolution was too bad, but also the quality was too bad. And also we are not sure if we can trust the upward-looking DVL. So we have, all those surveys that I showed were near the seabed. So we used the downward-looking DVL, but we also have an upward-looking DVL. And we haven't tested it in action in a sharp situation. And we also have no data on what accuracy you get with the navigation. Presumably you get a little bit worse than the downward-looking DVL because it's ice and not rock. Since we don't know, we can't trust it in Antarctica. We need to know how good it is when we put it in the water there. So our deliverables for this year was to install and test new upward-looking multibeam, and we selected finally EM 2040, the Kongsberg, the same one that we have looking down, and also to test the upward-looking DVL. And luckily, we got a very tough winter here on the west coast. So this is the view out here. That's what it looked like in February. Everything here was ice covered, and we had to convert our regular research vessel to an icebreaker. And the ship crew, they enjoyed that very much. We are sailing the boat now, so it's fine to some students in Härnösand. Yeah, so very different. It felt very luxurious to be able to do ice tests here in our own backyard. It was much simpler logistics than Antarctica, but of course there are problems. So we normally have a container to put it in, but we can't fit that on our research vessel, so we had to, everything froze. It was really, really cold, minus 18 degrees. So cold for this location. So we had to cover up with blankets and pour hot water everywhere. And it was quite hard work actually to keep this from breaking. And we had, so it froze here, and then there was a stretch of open water, and then it froze further in. So what we did was that we launched in open water, and Ran swam in under the ice, and then did the ice tests, and then came back out. So this is after launching. And then we parked with the research vessel in the ice and lay there to wait. And you can see these structures in the ice. I don't know what caused them, but you see, maybe it's waves or something, big waves that came in, or some process in the ice. I really don't know. But the interesting thing is that we see them on the multibeam. So this is just a photograph of our screen. We have a software reflection that you can easily and quickly plot data to get the first view of it. So this was the first thing we saw when we got the first data of the multibeam. So this track here is the Marine's icebreaker that went in through the ice, and this is the bathymetry, and this is the backscatter from the upward-looking multibeam. And those, so as you see, we got the sun velocity wrong. This is not real. It's not thicker ice under Ran. It's you need to adjust that. But the structures that you see here, they are not caused by faulty. They are real. Those circles here, they are those circles that you see from the surface. So that was great. The resolution here is 1 decimeter. And as far as I know, no one has seen a survey of ice with that resolution before. I thought it was really interesting that you can pick up small structures. This is not old ice. It's not particularly thick. It's a few decimeters. And in this, near the ice edge here, this is the ice edge. It's even, I mean, this is partly slush. So it's not, you will get much thicker and much clearer ice in the polar environment. I was very excited how much you can see from it. Yeah, and you also see these structures. They are more visible in the backscatter data, actually, compared to, but you also pick up in the, this is depth here. They are a little bit thicker. I imagine the ice has been sort of pushed. And it had no problem to detect the ice as a surface. So we were hoping that we would get good results of the navigation. We were here for 2 weeks, and we were operating every day for 2 weeks. We ran missions every day and worked really hard. And we learned a lot. And what we learned is, because this hasn't been tested, Hugin is a well-tested vehicle, and we have serial number 58, so they are operated, but not under ice. So what we learned is that, understandably, now when we know it, Hugin is programmed to weight data from the upward-looking DVL extremely low. So what they have done is to add an artificial noise. They have done that not only in one place, but in several places, in order to reduce the quality so that it will discard it. And this is, of course, a safety precaution. If it locks on the sea surface, it can go completely wrong. It can go, off in a completely wrong direction and smash against a wall or something. So we understand why they have done it, but it was very hard to find all the places where this was done, and they were very helpful. They were on the phone with us every day. And then by setting, we managed to get it done and work around it. This took 2 weeks. And if we don't make these changes, it will not work. You think you have an operating upward-looking DVL, but it doesn't use that data at all. It's as if you didn't have a DVL at all. But you think you enable it when you start the mission, you put it in the mission plan. So Ocean Infinity, they are sort of indirectly in this group now. And I have heard that, I know that they have lost at least one vehicle under ice. And I don't think they did this. It's no wonder that they lost it. It was operating on inertial navigation mode when they did that. So for the navigation tests, I thought I would have a very nice map with the side view and so on. But at 1 o'clock last night, I gave up that idea. So here is just a screenshot of our of the position of the vehicle, and this is the ice here. So we were launching here, and then it went under ice, and then this is where the ferry goes to the ferry and breaks ice. So we passed under the open area of the ferry and turned around, and then we went out again. And we did this over and over again, several times every dive. And when altitude-wise, we went in near the seabed, and we had bottom track, but no ice track. And then we turned around, and when we went out again, we changed the altitude so that we came near the ice, and it could lock on the ice, and lost bottom track. And that was also a setting that we had to change. Normally, we have a 180-meter range for the DVLs, but we switched it to 20 meters, so to really simulate what will happen in Antarctica, where you have a 1,000-meter water column. So then the idea was that it would lock on ice on the way out, and then not go too far, and then it will pick up this C node. The C node, it knows where the C node is, and that has a large range, so it will get the navigation down. And yeah, so I just show you, this was one of the first. We did that over and over again every day. I think we have 7 missions, just exactly like this. So this is where we launched, and then so here is standard deviation of the position, horizontal position, and then you see it growing here slightly. Here we have bottom track, and then it's flat, it doesn't grow, and this is the area where we turn, so you have many turns, then you get smaller error too. And this is where we thought we would lock on ice, so you see the error skyrocketing. This here is 150 meters, and it's only been, that takes 10 minutes to get to an error of 150 meters. This is what happened to if you don't make these changes. Next one, we thought that we had enabled it more correctly, but we still had this artificial noise that we didn't know about. Same scale of error, 140 meters. Yeah, and you see, so launch, bottom track, turning, ice track, and then it goes down again, the error. That is when you get contact with the C node, and then repeat. And then finally, after many days and many hours phone call with Kongsberg, we got this. So now it's operating. This was the 2 last missions look like this, out of maybe 11 missions all in all. That was when we managed to get it out. So now you see the standard deviation here is 15 meters. And so here's the C node, bottom track, turning around. And this is as this lifts up. And then you have the ice track. Then you get the C node. So the ice navigation is slightly more uncertain. That's not like, it's much, much better than pure inertial navigation still. And we still had quite a lot of noise because we are worried that if you have a flat surface, there are no waves, maybe it will lock on the surface, and you really don't want that because the surface moves and you go wrong. We don't want this happening when we are not absolutely sure that there's fast ice above the vehicle. So there's still some noise, and that means there will still be some errors, more errors compared to the seabed. And the next Antarctic cruise will be in January to March 2022, when we go back to the same region. And our plan is to go, plan A is to go to exactly the same spot and use our old data and continue just to go further in those, and also visit the third trough that we couldn't get to now because we had to abort everything, and try to go to that eastern part at Pine Island, go enter the vehicle through and check where is the velocity highest. And this summer we'll have a workshop, a SMaRC workshop with students and young scientists to plan missions for Antarctica. So we will, everyone who's interested can join that. And the aim is to have a library with about 50 missions that we can upload when we are there. another thing that we learned on the Antarctic cruise is that it's hard to think when you've been at sea for a couple of months, and it's good to prepare everything that you can prepare in advance. Try to avoid improvising new missions with clever ideas on the spot. And yeah, we are very, very glad that we had this nice ice winter. We could do all our tests. We didn't think we would be able to follow all these in but yep, that's it for me. Thank you for listening.